Scientists made electricity out of thin air using bacteria pulled from river mud. That's not clickbait. It happened in 2020, it got covered by BBC, The Washington Post, and Newsweek, and it was real. But here's the part almost nobody knows. 3 years later, the same team found something even bigger, something that basically threw out everything people thought the discovery was about. And that second finding barely made a sound. So today I want to walk you through the whole thing. Where this bacteria came from, how a random accident in a lab turned into a working device, and why the biggest twist in this story got almost no attention at all. This isn't some sketchy YouTube free energy gadget you build in your backyard with a copper pipe and a diode. This is a peer-reviewed paper published in Nature, one of the most respected science journals in the world. Real researchers, real data, real measurements. And once you hear how it actually works, you'll understand why this story deserves a lot more attention than it got. Let's start with the problem this whole thing is trying to solve, because that's where the story actually begins. For decades, if you wanted power without plugging into the wall, you had two real options: solar panels, which need sunlight, or wind turbines, which need wind. Both are great, but both have a huge weakness. They stop working the moment the condition they depend on disappears. No sun, no power. No wind, no power. That's a problem for anything that needs to run constantly, especially small devices like sensors, wearables, or anything placed somewhere that doesn't get direct sunlight or wind, like indoors, underground, or in a desert. Scientists had been trying for years to pull power from a source that never really goes away. And there's one thing that's almost always present, no matter where you are on Earth: moisture in the air, humidity. Even in the driest places on the planet, there's some water vapor floating around. The problem was, nobody had figured out how to turn that moisture into a steady, reliable stream of electricity. People had tried before. Some devices could generate a small burst of power from water vapor, but it would last less than 50 seconds before it stopped working. That's not usable. That's a party trick. So the real challenge was this: could anyone build something that pulls electricity from humidity in the air and keeps doing it continuously, day and night, without stopping? This is where the story gets interesting, because the answer came from somewhere nobody expected. Back in the late 1980s, a microbiologist named Derek Lovely was studying mud. Specifically, mud from the Potomac River. He wasn't looking for anything related to electricity. He was studying bacteria that live in sediment. But in that mud, he found something strange. A type of bacteria called Geobacter sulfuroducens. This bacteria belongs to a small group nicknamed electrogens, because they have this unusual natural ability to move electrons around, almost like they were built to conduct electricity on a microscopic level. Lovely kept studying this bacteria for years. At some point, his lab discovered that Geobacter can grow these tiny hair-like structures called protein nanowires. Think of them like microscopic wires, except instead of being made from copper or metal, they're grown by a living organism. For a long time, this was just an interesting biological fact. Nobody knew what to actually do with it. Fast forward more than 30 years. Derek Lovely is now at the University of Massachusetts Amherst, and he starts working with an electrical engineer named Jun Yao. Yao had spent years at Harvard working with silicon nanowires for electronics. The two of them wanted to see if these bacteria-grown protein nanowires could be used to build something useful. Now here's where it gets good. The discovery that changed everything wasn't planned. It wasn't the goal of the research. It happened by accident. A PhD student in Yao's lab, named Xiaomeng Liu, was working on a completely different project. He was building a sensor device using these protein nanowires, something totally unrelated to generating power. But while testing it, he noticed something weird. The device kept producing a small electrical current that shouldn't have been there. At first, that probably looked like a mistake, some kind of error in the setup. But instead of dismissing it, he investigated further. What he found was that the current only showed up when the device was exposed to humidity in the air. The protein nanowire film was actually absorbing water vapor, and that was creating a voltage across the device, all on its own, with nothing else needed. No battery, no sunlight, no wind, just air. That accidental discovery became the foundation of what they now call AirGen, short for air-powered generator. So let's break down what's actually happening inside this thing, because it's simpler than it sounds. Picture a super thin film, thinner than a sheet of paper, made from a layer of these protein nanowires. This film is less than 10 microns thick, which for reference is thinner than a human hair. This film sits on top of one electrode. Then a second, smaller electrode sits on top of the film too, but it only covers part of it, leaving some of the film exposed directly to the air. Here's the key part. Because part of the film is covered and part of it is exposed, the exposed section absorbs more water vapor from the air than the covered section. That creates an imbalance. One side of the film has more moisture built into it than the other, and that imbalance in moisture creates an imbalance in electrical charge between the top and bottom of the film. The researchers compared this to how a cloud works. Inside a cloud, water droplets carry different amounts of charge depending on their position, and that difference in charge is part of what eventually creates lightning. This device is doing something similar on a tiny scale, just using a solid film instead of a cloud. The charge difference between the exposed part and the covered part of the film generates a small, steady electrical current between the two electrodes. And unlike previous humidity-based devices that would fizzle out after less than a minute, this one kept running continuously. The researchers tested it, and it kept producing power nonstop, hour after hour, day after day. Now let's talk numbers, because I want to be honest with you about what this thing actually produces. This is not going to replace your power company anytime soon. The device produced about half a volt of sustained voltage and a current density of about 17 microamps per square centimeter. If those numbers don't mean much to you, here's the simple version. This is enough to power very small electronics, like tiny sensors or small LED and LCD displays. It is nowhere close to powering a phone, a laptop, or anything in your house. This is small-scale stuff. But the fact that it worked at all, continuously, indoors, without sunlight or wind, even in extremely dry environments like a desert, was a big deal. That's what made it worth publishing in Nature back in February of 2020. And when it published, it made headlines everywhere. BBC covered it. The Washington Post covered it. The Guardian, Newsweek, USA Today, Smithsonian Magazine, all of them ran stories on electricity made from bacteria. Jun Yao was quoted saying, "We are literally making electricity out of thin air." It was a strong headline, and it deserved the attention. This was a real discovery, backed by real published research, not some gadget being sold online. So if the story ended there, that would already be interesting enough for a video. But it doesn't end there. And this is where things take a turn that almost nobody talked about. 3 years later, in 2023, the same research team published a second paper. And this one basically rewrote what everyone thought the first discovery was actually about. Here's the problem they had been sitting with. The bacteria-based nanowires worked, but growing enough of them to scale this up into something bigger was slow and difficult. Bacteria don't grow instantly, and producing large quantities of these nanowires for bigger devices was a real bottleneck. So the team started digging deeper into why this effect worked in the first place. Was it something special about the bacteria itself? Or was there something else going on? What they found completely changed the direction of the research. It turned out the bacteria weren't actually the essential ingredient. What mattered wasn't that the material came from a living organism. What mattered was the physical structure of the material. Specifically, tiny pores smaller than 100 nanometers wide. For comparison, that's about 1,000th the width of a single human hair. They tested other materials that had nothing to do with bacteria at all. Wood, silicon, different materials engineered with these same tiny pores. And it worked. Nearly any material, as long as it had pores smaller than that 100 nanometer threshold, could pull the same kind of continuous electricity from humidity in the air. Think about how big that is for a second. The original story was, we found a special bacteria that can generate electricity from air. The real story, the one buried underneath, is almost any material on Earth can do this, as long as you shape it the right way. That's not a small footnote. That's the actual bigger discovery. And it barely made a ripple compared to the first one. Why did that happen? A few reasons, and they're pretty simple once you think about them. The first paper landed in Nature, one of the most high-profile science journals that exists, the kind of place that guarantees mainstream press attention. The second paper landed in a journal called Advanced Materials, which is respected in the scientific community, but doesn't get the same kind of mainstream media pickup. On top of that, we found a weird bacteria that makes electricity is a much easier headline to write than we discovered a general physical principle involving nanopore structures. One sounds exciting and simple. The other sounds like a chemistry lecture, even though it's actually the more important finding. There's also the fact that there was still no product to show for it. No gadget you could hold up on camera. No price tag. No release date. Journalists, and frankly YouTube algorithms too, tend to reward stories with something tangible attached to them. A discovery about pore size, without a consumer product behind it, just doesn't spread the same way, even when it's scientifically bigger news. So where does this leave things today? The research hasn't stopped. The same lab has continued building on this work, including experiments with devices called memristors, which are components that can mimic some aspects of how the brain processes information, and self-powered sensors that generate their own tiny bit of electricity while also doing simple computing tasks, all without a battery. The University of Massachusetts Amherst has also continued funding this research through internal grants aimed at eventually pushing it toward commercialization, with hopes of eventually attracting bigger funding from places like the Department of Energy. There's also a newer development worth mentioning. A student team at UMass Amherst formed a startup-style venture built around this research, and in 2025, that team won UMass's Minute Pitch competition and the campus round of the Holt Prize, which qualified them for the national competition. That's a real, current thread tied to this technology, but it's important to be clear about what that actually means. This is a student venture at an early competition stage. It is not a finished product sitting on a store shelf. As of right now, there is no consumer airgen device you can buy, and I think that honesty matters here, because this topic gets dragged into some really questionable territory online. You've probably seen videos claiming you can build a free energy antenna out of a copper pipe and a diode for $25, pulling hundreds of thousands of volts straight out of the atmosphere to power your entire house. That's not this. That's a completely different claim, dressed up to sound like real science, usually mixing in unrelated facts to make it sound credible. What we just walked through is the opposite of that. It's small. It's slow. It took over 30 years from the original bacteria discovery to a working device. The output is tiny, measured in microwatts, not kilowatts. But it's real. It's published, it's been tested, and it's still being built on today. Sometimes the real science is stranger, and honestly more impressive than the fake version people already believe. A bacteria pulled out of river mud in the 80s. An accidental discovery by a student working on something completely different. A device that runs nonstop on nothing but the moisture already sitting in the air around you. And then a second discovery, even bigger than the first, that almost nobody heard about because it didn't come with a flashy headline attached. That's the story. Real, documented, and still unfolding right now in a lab that most people have never heard of. If you want to dig into the actual research and sources behind this, I put everything in the description.